Those who man our ships must be physically fit and mentally alert. And one of the requirements for physical and mental fitness is proper atmospheric conditions in the close confines below deck. Berthing, messing, and working spaces must be habitable at all times. With modern naval vessels, this presents many difficult problems. Air accesses are limited in number, and most of them are closed under darkened ship conditions. Steel boundaries exposed to the sun conduct heat to the interior, even though insulated from within. In addition, heat and moisture are generated below deck by the power plant, by electronic equipment, and also by the men in the ship. Of course, a large crew means large laundries, galleys, and additional heat-producing services. Before going into methods for controlling atmospheric conditions aboard ship, let's examine some of the basic principles upon which these methods are based. 5 factors which affect the comfort and efficiency of the crew are the temperature of the air, its relative humidity, air motion, an adequate supply of oxygen, and freedom from objectionable odors or fumes. Under normal conditions aboard ship, adequate control of temperature, relative humidity, and air motion will automatically ensure an adequate supply of oxygen and freedom from objectionable odors. We are therefore primarily concerned with only these 3 factors. Now, let us consider a typical space immediately below a weather deck. One of the things influencing living conditions in such a space is radiant heat from the sun. Some of this heat radiates directly to the space, and some is picked up by air currents within the space. Additional heat is produced by electronic equipment, by electric lights, and by the bodies of the crew. As heat and moisture within a space accumulate, the temperature and humidity rise rapidly. Unless adequately taken care of, these conditions will adversely affect personnel. For efficient performance, the human body must keep itself at the normal temperature, about 98.6 degrees. The body maintains this temperature by giving off excess heat. The more active the body is, the more heat it gives off. So long as the surrounding air is at a lower temperature than that of the body, heat will pass from the body to the atmosphere. If the air becomes too cold, the body loses too much heat and becomes chilled. Then heat must be added to the space or additional clothes put on to conserve body heat. As the temperature of the air rises, the difference between it and the body temperature becomes less and less, so the body gives off excess heat at a decreasing rate. But the body has another means of cooling itself. It perspires, and the body is cooled as the moisture evaporates. Even though the temperature of the space may go above body temperature, the body can continue to give off heat only so long as the moisture continues to evaporate. In still air, an envelope of saturated air forms around the body, limiting the amount of heat and perspiration the body can give off. If the air is set in motion, this envelope will be dissipated, and heat losses from the body will increase. When the air ceases to absorb heat and moisture, the body cannot get rid of its excess heat. Its heat balance is upset, and serious physical disorders may follow. It can be seen how important the control of temperature, humidity, and air motion is to efficient body performance. Now, let's see how adequate atmospheric conditions are provided aboard ship by means of ventilating, heating, and mechanical cooling systems. In a typical ventilation system, outside air is conducted to and from below-deck spaces through a network of ducts. Air enters through ventilators or deck house openings. it is forced through the ducts by fans, delivered through a series of supply terminals, and circulated through individual spaces where it takes out heat, moisture, fumes, and odors. Exhaust fans draw the warm, used air through the exhaust terminals and ducts, then discharge it through exhaust ventilators or deckhouse openings to the outside. Exhaust outlets are provided in the spaces having supply outlets, or are located in water closet spaces, pantries, and passageways adjacent to those spaces. Bracket fans are usually provided in living spaces to improve air circulation within the compartments. The larger size ventilating fans have two speeds: low speed for use when space heating is required, and high speed for warm weather conditions when more frequent changes of air are needed. Based on space usage, the temperature of ventilated spaces is determined by the amount and temperature of the air supplied. For example, the ventilation design for berthing spaces is based on air quantities to give an inside temperature in hot weather of 7 degrees above the outside temperature, the best that weight, space, and other technical considerations will permit. If the temperature of the outside air is 88 degrees, the temperature in the berthing spaces should be no more than 95 degrees. Obviously, in extremely hot areas, ventilation air alone is inadequate. The installation of additional bracket fans will help, as well as frequent wetting of decks exposed to the sun. In very hot spaces such as engine rooms, laundries, galleys, and pantries, it is not practical to maintain satisfactory temperatures throughout. So a high-velocity blast of outside air is directed toward operating stations, creating an area of cooler, turbulent air into which personnel can step for relief. Machinery spaces are provided with a greater rate of exhaust than supply, creating a slight negative pressure which prevents hot air from escaping to nearby living and working spaces. The operation of supply and exhaust fans should always be coordinated to ensure this negative pressure. In compartments where combustible vapors present fire hazards, exhaust ducts are equipped with flame arresters. If fire breaks out adjacent to the ventilator or weather opening of an exhaust system handling combustible fumes, and flames spread back through the ductwork, the arrestor will prevent the passage of flames into the space. Wherever practicable, the system which supplies air within the ship for ventilation also provides heated air in cold weather. The first stage of heating takes place in a preheater, which is installed upstream of the fan in the ductwork, usually near the intake. Air passing through the preheater is warmed as it flows by these steam-heated fins. The amount of steam entering the preheater is regulated by a control valve having two thermostatic bulbs, one on the inlet side of the heater and the other on the discharge side. When the outside temperature goes down to 35 degrees, the first bulb opens the steam valve, permitting steam to flow into the heater up to 25% of its capacity. This protects the heater against freezing. The second bulb, which controls the remaining 75% of capacity, is set to bring the air temperature up to the desired preheat temperature, usually about 50 degrees Fahrenheit. Air which has been preheated only is directed to inherently warm spaces such as galleys and laundries. Since living, berthing, and working areas may require a higher temperature, preheated air is passed through a reheater, similar in design to a preheater. One reheater sometimes serves a number of spaces called a zone, within which heat load requirements and weather exposures are similar. A room-type thermostat operates a valve which controls the steam flow through the reheater. Medical studies show that the thermostat in living compartments should be set at no more than 70 degrees Fahrenheit, and preferably between 65 to 68. In some installations, a combination heater serves as both a preheater and a reheater. In this case, the steam valve is controlled by a thermostatic bulb located on the inlet side and by a thermostat located in the compartment which is heated. Where it is not practical or desirable to provide heated air through the ventilation system, unit, convection, or electric heaters provide the space heating. We have seen how ventilation in itself cannot produce satisfactory space conditions with extremely high outside temperatures. It is therefore essential that a more effective means be used to cool vital spaces. This is accomplished by a mechanical cooling system which cools and recirculates the air. Its elements include an air intake, air filters, a cooling coil, a fan, distributing ductwork, and terminals. A reheat coil is also included for adding heat to the space in cold weather. Cooling is accomplished by circulating a refrigerant, such as Freon or chilled water, through the cooling coils. The refrigerant is supplied from a centrally located refrigeration plant, and its flow to the coil is regulated by a solenoid valve controlled by a room thermostat. The fan moves the air past the coils, through the ductwork and terminals, and circulates it throughout the space. This cycle is repeated continuously. Near the air intake of the system is a replenishment air terminal, feeding a small amount of outside air for oxygen replenishment and dissipation of odors. An equivalent amount of air is exhausted from the space. In magazines, handling rooms, and similar spaces, cooling is accomplished by gravity cooling coils hung from the overhead. Air is cooled as it flows by the coils in natural convection currents. In such spaces, replenishment air is admitted only at periodic intervals as directed by the damage control officer. Shipboard mechanical cooling systems are designed to maintain a space temperature of 85 degrees and a relative humidity of approximately 50% when the outside temperature is 88 degrees. When all heat-producing sources anticipated in the design are not present, or the outside temperature is lower than 88 degrees, a lower space temperature can be obtained. For mechanical cooling systems to work efficiently, accesses to the weather and to uncooled zones must be kept closed as much as possible. It is current practice to mechanically cool vital spaces such as CICs and sick bays. Berthing and other living spaces may be included, depending upon the size of the vessel, the climate in which it is expected to operate, and so on. Since the limitations in space and weight of equipment aboard ship are so severe, the selection of spaces to be cooled must be guided by tactical, medical, and technical considerations. A shipboard ventilating, heating, and cooling system is no better than its maintenance. A great quantity of air passes through its elements and accumulates dirt. This cuts down airflow and impedes heat transfer. For example, a 50% reduction in air quantity due to a dirt-matted screen will result in a space temperature as much as 10 degrees higher than intended. Furthermore, dirt obstructions change the flow characteristics of fans and contribute to added noise. Also, serious fire hazards are created by clogged grease filters in galleys, by dirty filters ahead of flame arresters, and by dirt accumulations in ducts. It is essential that each ship set up a definite schedule of inspection and maintenance as recommended in Chapter 38 of the Bureau of Ships Manual. Inspection requirements vary for different elements of the system. For example, laundry exhaust screens, where lint accumulation is a serious problem, should be inspected once a day. Heating and cooling coils should normally be inspected once a week. Other elements, such as ducts, where dirt accumulates more slowly, may require inspection only twice a year. Fans should also be lubricated on regular schedule. In many cases, new fans have been in storage for months or even years, thus causing possible deterioration of the lubricating quality of the grease. If unchecked, bearing and motor failures will result. Only authorized personnel should maintain, adjust, and repair the air conditioning system. Unauthorized personnel should never attempt to obtain additional cooling effects by piercing ductwork. This may create a serious hazard where watertight ductwork is involved. In this film, we have shown the basic principles which govern the operation of shipboard ventilating, heating, and cooling systems. We have dealt with the factors which influence the condition of the air and the part these factors play in the well-being of personnel. We have seen the elements of typical ventilating, heating, and mechanical cooling systems and how they operate. We have shown the importance of a ship's maintenance schedule which must be observed for best results. A sound grasp of these principles of operation will assist in maintaining proper atmospheric conditions below deck and will contribute to the well-being and the fighting efficiency of all the men who man the ship.